Alright, so in this video I'm gonna be explaining another important article with the title Multi-Source Domain Adaptation with Collaborative Learning for Semantic Segmentation. This paper in 2021. Multi-source unsupervised domain adaptation aims at adapting models trained on multiple labeled source domains to an unlabeled target domain. In this paper, we propose a novel multi-source domain adaptation framework based on collaborative learning for semantic segmentation. Firstly, a simple image translation method is introduced to align the pixel value distribution to reduce the gap between source domains and target domain to some extent. Then, to fully exploit the essential semantic information across source domains, we propose a collaborative learning method for domain adaptation without seeing any data from target domain. In addition, similar to setting of unsupervised domain adaptation, unlabeled target data is leveraged to further improve the performance of domain adaptation. This is achieved by additionally constraining the outputs of multiple adaptation models with pseudo labels on line generated by an ensembled model. You see the multi-source domain adaptation for semantic segmentation. The left shows synthetic images. For example, GANs are very good to produce synthetic images, GANs. And so the left shows synthetic images and corresponding labels generated from different simulators, which suffer domain shift between each other, but share semantic context. On the right shows unlabeled target image so these are real images. You see the overall framework. It has three components. It has image-to-image translation. So we translate this image to another image. It's an image-to-image translation based on lab color space. A collaborative learning between source and domains, and a collaborative learning on a target domain. The solid arrows you see represent the forward data flow, and different colors indicate different source domains or target domain data flow. The dashed arrow represent the supervision to network output. So we just show the case of two source domains as an example. We observe that the domain discrepancy between domains mainly lies in appearance of images, color, and texture. For example, the appearance discrepancy between the two source domains, GTA 5 and Cynthia, and between source domain and target domain. You see them here and in figure 1. So this discrepancy would further increase the difficulty of multi-source domain adaptation. An effective style transfer could reduce this discrepancy to some extent. For simplicity and efficiency, we propose an image translation method that translates the style of images in source domains to the style of target domains by aligning the distribution of pixel values. Finally, we translate the converted lab image from source domains to the style of target by shifting the distribution of pixel values to the image of target domain. So because we have the mean and the standard deviation of this converted target image, we can do this translation. After aligning distributions, we then convert the translated image from source domain back to RGB color space. So assume there are n different labeled source domains, which are sampled from n IID distribution and n deep networks of the same architecture, but different weights learned on these source domains. Then for a model M sub S sub I, the learning process of model is supervised by segmentation loss on labeled data from source S sub I, and collaborative loss on output from source S sub K and K. And we use this simple cross entropy for loss of your segmentation. And we also use this callback library divergence. For example, what is a callback library divergence between F sub Sk and F sub Si? Because for F sub Si, the subscript indicates that F is generated by M sub Si, while the superscript F is the feature computed for images from domain S sub K, and C is the number of categories to be segmented. In practice, unlabeled data is often relatively easy and cheap to collect. Moreover, models trained on the data of target domain can learn better features and perform well on target domain. Therefore, we propose a collaborative learning method to fully take advantage of unlabeled images in the target domain and further boost the performance of models on target domain. Denote target domain as T, which has collected large amounts of unlabeled images. For an image X sub T in the target domain, we first feed it to all of n models and compute the corresponding outputs of models for the input image. Outputs of these networks are ensembled and the softmax function. This softmax function, sigma, is used to compute the probability map. We generate one hot pseudo labels Y hat. So this term is designed to prevent poor predictions of target images in the early training process, collapsing the network training. Because Kerr is the current iteration and maximum iterations of training process. And you see what happens when we go from this source domain to these target domains for different methods. This is the validity of proposed image translation method. The performance comparison with recent single source unsupervised domain adaptation trained on images before and after translation. So after translation, we have this amount of increase. So these are the data sets. For example, this one has urban traffic scene images. This is synthetic game engine, synthetic images from game engine. And this one is photorealistic frames rendered from a virtual city.